Now I'd like to look at the effect of molar mass on boiling point. As molar mass goes up, so does London dispersion forces. It increases and boiling point goes up. So let's look at some examples. Hydrogen, for example, is diatomic. It's covalent molecule and extremely light. Its molar mass is 2 grams per mole. Boiling point is minus 252. What do I have to offer? Since I'm nonpolar, only London dispersion. Now we'll go to a bulkier and heavier molecule, nitrogen. Nitrogen is also a nonpolar, but its molar mass is much higher. It's 28 grams per mole. So you see the boiling point is being increased. From negative 252, we have gone to negative 196. What do we have? We still have London dispersion, so the only effect is molar mass. Let's go to chlorine. Two chlorine single bonded to each other, non-polar again, and molar mass is much higher, 71, and you see the boiling point increases and you only have London dispersion. Now if you look at H2O, its molar mass is only 18, so it's somewhere between hydrogen and nitrogen, but its boiling point is 100 degrees Celsius, which is the highest. So the question is why. So if you look at H2O, it's a molecule that is bent, and that makes it polar. The direction of polarity is toward oxygen. That's your dipole moment. And because you are polar, and this polarity is known as hydrogen bonding, so you have hydrogen bonding, and that increases your boiling point. Now one thing you should realize is if you have hydrogen bonding, that means you are polar. That means you also have London dispersion. So your argument in a case like this should be hydrogen bonding. Looking at other examples, now this time instead of nonpolar, I have polar molecules, all group 7 halides, hydrogen chloride, hydrogen bromide, iodide, and fluoride. And these are, if you put hydrogen next to that halogen, this is the negative side, the positive side, the dipole moment goes toward the halogen. And if we look at molar masses, you see that the molar mass goes up for hydrogen bromide compared to hydrogen chloride, and its boiling point increases. What do you have? You have London dispersion. You also have dipole-dipole in both cases. So dipole-dipole, dipole-dipole. But since they are both polar, I'm going to use as my argument the molar mass goes up, the London dispersion is increased, therefore you have higher boiling point. Now hydrogen iodine, bulkier, heavier, its molar mass is higher. Then again you are also, same notion, you are polar, so you have dipole-dipole. But then again in my argument I'm going to say since your molar mass is higher, your London dispersion forces is higher. Now if you look at hydrogen fluoride, it's only 20 grams per mole, and it's even lighter than HCl. But if you look at its boiling point, it's the highest, and the question is why. Hydrogen fluoride is also polar, but it's a polar bond that is known as hydrogen bonding because it's attached to fluorine. Therefore that's what it makes this molecule extremely sticky, and when they line up to another hydrogen fluoride, they are going to hold on to each other much stronger than other hydrogen halides, and that's why the boiling point goes higher. So in my argument we are going to use hydrogen bonding. In your argument you should also do the same. Looking at some other examples, this time I'm posing a question. Which of the following has higher boiling point? Their molar masses is very close, these three compounds. The first one is C3H8, so when you do Lewis dot structure, it looks like this. And then you have to be able to say what sort of bonding you have. Do you have London dispersion? Every compound has London dispersion. Do you have polarity? No. If you don't have polarity, you also don't have hydrogen bonding. If you look at the next one is aldehyde. When you do Lewis dot structure for that, you see there is a double bond O, hydrogen, hydrogen, hydrogen. Do I have London dispersion? I do. But you also have another thing. You have a polarity going for yourself because of the oxygen. So this is also polar. Let's do the last one as examples, which is an alcohol. It's CH3, CH2, and then you have OH. So now you have London dispersion. Everybody has London dispersion. You are polar, but this is a polarity, extreme of polarity, which is known as hydrogen bonding because hydrogen is attached to oxygen. So this has hydrogen bonding. So which one has, this is the highest boiling point, and for this, the boiling point is actually 78 degrees Celsius. This one is the next boiling point because of the polarity, and its boiling point is equal to 20.2 degrees Celsius. This has nothing except London dispersion forces, and its boiling point is the least. And it's a gas, so it's less than room temperature, negative 42 degrees Celsius. Similar question. This time I have two alcohols and one carboxylic acid, and molar masses is also offered. So let's just see when we do Lewis-Dot structure what they look like. So alcohol looked like this. This is the first alcohol. The second alcohol has one more carbon member. They are homologous series, CH, and then OH. If we slow down here, this alcohol here has a higher molar mass compared to this, so they both have London dispersion. They are both polar, and they both have H bonding. But what you should be able to say is, since they are the same family of alcohol, same H bonding, we are going after London dispersion. This one is heavier, more molar mass, more London dispersion. If we do the carboxylic acid, it's CH3, C double bond oxygen, single bond oxygen H. Here I still have London dispersion. I have polarity, I have H bonding, but what you have is two polar sides. There is one hydrogen bonding here. There is also one for this. So this should have the highest boiling point, and its boiling point is actually 118 degrees Celsius if it's pure. This one is in between, has the second higher boiling point, and its boiling point is 97 degrees, and this one has the least of the boiling point, and it's 78 degrees Celsius. So that's how your judgment should be. Now the next set of questions, I simply have few things to see if you recall before going to physical properties. Which of the following bonds are polar? So we do the Lewis-Dot structure. You look at the periodic table, you see the location of each individual iodine versus chlorine, and I'm going to say this side is negative, this side is positive, because chlorine is closer to fluorine, so this is polar. If we look at hydrogen cyanide, we have done it quite often, a triple bond here. Now carbon and hydrogen have the same electronegativity, so but we go after carbon versus nitrogen, which nitrogen is very electronegative, so this one is polar. The direction of polarity is toward nitrogen. BCl3, boron only needs 6 electrons, so it looks like this. Now it's a symmetrical shape. Chlorine is pulling on boron in every possible direction, so this is non-polar. CH2F2, it's a tetrahedral, and when you put your 4 attachments, fluorines line up on one side, so this is direction of polarity, and you are polar. To do SiF4, silicon is in between, tetrahedral, 4 fluorines. Now each fluorine is pulling you on on its direction. So silicon is being pulled on 4 directions equally. They cancel each other out, symmetrical. This is non-polar. Finally, if we do NF3, it is a pyramidal, trigonal pyramidal, and nitrogen is pulling all these hydrogens, electrons toward itself. So it's extremely polar. I actually did ammonia by accident, but NF3 has the same sort of a shape. And what happens this time, NF3, fluorines are more electronegative. So direction of polarity changes is this way rather, but it's still polar. The next set of questions is to see if you recall which is hydrogen bonding, but you have to do Lewis dot structure. CH3OH is, HO is this. Since hydrogen is not attached to oxygen, we are going to say there is no hydrogen bonding for this. The next one, if you do, this is example of a ketone. Lewis dot structure you should be able to do for it. CH3s. Now, does it have hydrogen attached to the oxygen? No, it doesn't, so there is no hydrogen bonding. The next one is a carboxylic acid, C double bond O, OH. Is hydrogen attached to oxygen? Yes, it is here, so it has H bonding. The next example is an ether, CH3 attached to oxygen, another CH3 to end it. The question is hydrogen attached to oxygen? And you see there is none in this molecule. I don't have hydrogen bonding. The next one is methyl amine, and when you do it, there's CH3, NH2, a lone pair here. Is hydrogen attached to nitrogen? Yes, it is. Therefore, this has hydrogen bonding, H bonding. So yes. The next one is amide, and if you do it, CH3, C double bond O, N, it ends in nitrogen with two hydrogens attached to it. Is hydrogen attached to nitrogen? Yes, it also has H bonding. So hopefully by now you sort of have been exposed to what hydrogen bonding is. It should be attached to oxygen, nitrogen, or fluorine within a compound. Then you have example of hydrogen bonding.